In this session, I will discuss about the various terms plume, mixing depth, and also what are the different types of plume behaviors. So, a plume can be defined as the dispersed path of gaseous pollutants or gaseous effluent released from the stack into the atmosphere. That is, the path of the gaseous pollutants or the path of effluent once it is emitted from the source. Okay, so that dispersed path is said to be a plume. And due to the outlet velocity momentum and the buoyancy effect, the plume rises from the stack or chimney, and it will rise to a certain height, and the movement of these gaseous effluents is almost visible in the atmosphere. That is, the plume rise, it will be almost visible in the atmosphere. And as well as the main two forces that is responsible for plume rises, buoyancy effect and momentum rise. So next, discussing about mixing depth. Mixing depth actually means the height of 100 to 500 meter above the ground level where the pollutants gets mixed up. Okay, that height is known as the mixing depth. So the pollutants released from industrial stacks, they get mixed up at a height of 100 to 500 meter above the ground level, and depending upon the meteorological factors, that is the wind, velocity, as well as the atmospheric pressure, and also the humidity or the moisture that is present in the atmosphere, the mixing of pollutant happens. And this vertical depth where the pollutants are diluted and dispersed in the available atmospheric condition is called the mixing depth. So this 100 to 500 meter above the ground level at which the pollutants get mixed up depending on the atmospheric condition is known as mixing depth. And the plume height, it should not be lower than the mixing depth. Okay, and it is better to provide the plume height while designing the stack. The plume height should be such that we will discuss about the various design parameters or the various formulas that are used for designing the stack height as well as the height of the plume. So plume height should not be lower than the mixing depth. Okay, if the plume height is lower than the mixing depth, then the pollutants cannot get completely dispersed. So the plume height should be much greater than the mixing depth, so that the pollutants will not reach the ground level. Now, plume behavior, the very important concept is plume behavior. There are various types of plume behaviors, and it is very important from exam point of view. So, plume behavior actually means the critical relationship. A critical relationship exists between the atmospheric stability and the pollutant concentration, and depending upon these two relationship, that is the relationship between the pollutant concentration and the atmospheric stability, the plume behavior in a particular atmospheric condition are of different types. So it actually depends upon the meteorological condition, the vertical temperature gradient, okay, which actually varies from day to days or from season to season and between day and night. So the pollutants that cannot be transported or dispersed into the upper atmosphere, they will get trapped at the ground level, and it is very dangerous to human health. So there are several types of plume behavior depending upon the various atmospheric stability conditions, that is whether the atmosphere is stable or unstable, or whether there is an inversion existing. So based on all these factors, the plume behaviors are classified into behavior is classified into seven different categories, that is looping plume, fanning plume, neutral plume, conning plume, lofting plume, fumigating plume, and trapping plume. Okay, so now we will discuss each of these different plume behavior. So first one is looping plume. So a looping plume, it has a wavy character. So a diagram is given below, in which on the y-axis we have the height, and on the x-axis the temperature is there. So the very first diagram is about the internal energy diagram, and thereafter the relation or the lines indicating the ELR and ALR lines. Okay, and after that the dispersed path of the effluent is shown. Okay, so here you can see a wavy appearance for the plume. Okay, so it is having a wavy character, and this kind of plume behavior usually occurs in a super adiabatic environment which produces highly unstable atmosphere. Okay, usually super adiabatic lapse rate is associated with an unstable environment in which ELR is more than ALR. So if the atmospheric stability is unstable, then it will usually result in high turbulence that is prevailing in the atmosphere, and thereby it will lead to rapid mixing up of the pollutants. Okay, so the rapid changes in temperature and pressure, it results in the plumes to appear billowing and puffy. Okay, so thereby a wavy character we can see. And while unstable conditions are usually favorable for pollutant dispersion, higher concentration of pollutant can even reach the ground level. In the diagram you can see some of the waves may even reach the ground level. Okay, so due to this unstable, even though unstable conditions are favorable for pollutant dispersion, the high concentration, it will force the pollutants to ground level, and this kind of behavior can occur on sunny days with light to moderate winds, which will combine with the rising and sinking air and will cause the stack gases to move up and down and thereby have a wavy pattern. And in areas where environment is super adiabatic, providing higher stacks is one of the method to prevent the contact of pollutants from the ground. Okay, so looping plume, it happens in unstable environmental condition or atmospheric condition, and it is having a wavy character, and some of the waves can even reach the ground. So in order to prevent the pollutants from reaching the ground, it is better to provide a high rise stack, or by increasing the height of the stack, the pollutants can be prevented from reaching the ground. Second one is the fanning plume. Fanning plume, it occurs under extreme inversion condition. Inversion term we have already discussed. The term inversion means it happens due to it happens when the warm air lies below the cold air, or when temperature increases with height. That is what inversion means. So, and it is associated with a negative lapse rate condition. Okay, so here when an extreme inversion condition is existing, then the effluent will spread only horizontally, so it cannot lift up. Okay, due to the extremely condition, due to extreme inversion condition, the pollutants cannot lift upwards, but instead it will be spread, it will be dispersed horizontally. So because atmospheric pressure is stable, there is neither a tendency for the emissions to rise or it cannot descend. Okay, so thereby it will be spread horizontally. And the fanning plumes, they are more common in early morning hours just before the sunrise, and when there is light winds, and in areas where these inversions are caused by radiation inversion. If the inversion happens due to radiation inversion, that is providing a high rise stack can prevent the uh, kind of usual it can prevent the pollutants from reaching the ground. And in areas where subsidence inversion are occurring frequently, providing high-rise stacks are not practical and economical. So, this kind of inversion is actually not an ideal case. So, uh, providing a high-rise stack is not practical or economical in case of subsidence inversion, because subsidence inversion usually happens for much greater heights. Okay, that's about fanning plume. So it occurs under extreme inversion condition, and so the pollutants cannot lift upwards or it cannot descend downwards, and it will be spread horizontally. And this kind of fanning plume can happen due to radiation inversion or due to subsidence inversion. And if it is due to radiation inversion, then providing a high rise stack it will be better. Then if it is due to subsidence inversion, increasing the height of the stack is not a practical case. Why? Because subsidence inversion will happen for or it exists for much greater height. Next one is neutral plume. Neutral plume is the upward vertical rise of the plume from the stack, which occurs when the environmental lapse rate is equal to adiabatic lapse rate. So this kind of plume behavior happens when there is a neutral environment, that is when ELR is nearly equal to ALR. So there will be upward vertical rise of the plume. So this upward vertical rise will continue until the density of the air mass becomes equal to that of the and until the density of the plume becomes equal to that of the ambient air. Next one is conning plume. Conning plume, it happens when there is neutral or slightly unstable condition, and as well as when the wind velocity is greater than 32 km per hour and when cloud cover blocks the solar radiation. So under these conditions conning plume happens, and it also occurs under subadiabatic condition, that is when a stable environmental condition exists or when the lapse rate is subadiabatic, then the kind of plume behavior is said to be conning plume, and there is limited vertical mixing, only limited vertical mixing will be there, and hence the probability of pollution will be more, and it will happen this kind of plume will happen more on partly cloudy days and when there is alternate warming and cooling of the atmosphere. Now about lofting plume. Lofting plume, it exists under strong superadiabatic lapse rate above a surface inversion. So uh, till this till conning plume, the only one single environmental condition exists, that is whether it will be stable or it will be unstable or a complete inversion condition exists. Okay, and right from lofting plume onwards, two kinds of atmospheric conditions will be there. That is, here we have a there exists a strong superadiabatic lapse rate above a surface inversion. That is, an inversion is existing below. That is why you can see in the diagram, that is initially the temperature increases with height, that is it is an inversion condition, and above that inversion condition the uh, superadiabatic lapse rate exists. Okay, so that is superadiabatic lapse rate corresponds to an unstable atmosphere. Okay, so when the atmosphere is relatively stable, warm air remains above cool air and it creates an inversion layer, that is just below the stack, and the pollutants released below the inversion layer will remain trapped at the ground level, and in the absence of any atmospheric instability it will prevent the upward transport of the pollutant. So if an inversion layer is existing, then the pollutants will not get mixed up in that inversion layer. Okay, so here the inversion layer is below the stack, so the pollutants cannot come or it cannot get dispersed below the stack, so that the pollutants will not reach the ground level in this kind of lofting plume. Instead it will be mixed up, that is only in the unstable atmosphere it gets that in that unstable layer it gets mixed up. So there is minimum downward mixing up due to the inversion, but upward mixing will be quite turbulent. That is, if an unstable atmosphere is existing or a super adiabatic lapse rate is existing, there will be rapid mixing up of the pollutants. And if an inversion layer is existing, there will not be any mixing up. Okay, so the dispersion of pollutants will be rapid and no concentration will reach the ground. So this is considered to be the most ideal case for dispersion of air pollutants. So what we actually want is, for a better air quality, we must prevent the pollutants from reaching the ground. Okay, so that there will not be any ill effects. So this lofting plume is considered to be the most ideal case. Why? Because the pollutants get dispersed in an upper atmosphere, or above the stack the pollutants get dispersed and it will not reach the ground level when comparing with all the other kinds of plume behavior. Now about fumigating plume. When an inversion layer occurs at a short distance above the top of the stack and superadiabatic conditions prevail below the stack, that is just the opposite of lofting plume. Uh, if for just the opposite of lofting plume becomes the fumigating plume, that is inversion layer is above the stack and the unstable layer is below the stack. So as the unstable layer is below the stack, the pollutants get rapidly mixed up below the stack, so that the concentration of pollutants will reach the ground. And above the stack, inversion layer exists, so the pollutants will not mixed up above the stack. Instead it gets distributed below the stack, and it will reach the ground level due to the high turbulence in that region. Okay, so this is considered to be a very bad case of atmospheric dispersion, pollutant dispersion. So when an inversion layer occurs at a short distance above the top of the stack and superadiabatic conditions prevail below the stack, the plume is said to be fumigating, and here the pollutants will not escape above the top of the stack due to inversion, and they will be brought down near the ground due to the turbulence in the region above the ground and below the inversion. So it is considered to be a bad case. Now the very last kind of plume behavior is the trapping plume. So when an inversion layer exists above the emission source as well as below the source, so above and below the stack an inversion layer exists, and in between there exists a uh, stable or unstable atmosphere, and here it is an unstable atmosphere given. So when the in such a condition, the emitted plume will neither go upwards nor it will go down, and it will remain confined, or it will get mixed up within that two inversion layers. Okay, in the space between the two inversion layers, the pollutant gets mixed up. So this is considered to be a bad condition for dispersion, as the pollutants will not get uh, diffused into the upper atmosphere. Okay, so trapping plume is also a very bad condition for atmospheric dispersion, as well as fumigating plume is also a very bad condition, and lofting plume is considered to be the most ideal condition. Okay, so in this particular video, I think you might have understood about a plume, mixing height, and as well as the various types of plume behaviors. Thank you.